I'll begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I thank you for the students, for the weekend we just completed. Just help us to glorify you what we do this time, Lord. In your name I pray. Amen. All right, so I owe you some proofs of... What's that?
I said, don't you owe us some quizzes before that?
Is today a math battle day? I don't think so. And we're getting there. But yeah, I will probably rain quizzes upon you sometime very soon. But that time is not quite yet. Okay, so what I want to do is describe to you why this is a baby Stokes. Which I call baby Stokes. And the reason I call this baby Stokes is I want to consider the case that I have something like a polygonal region. All right, so it's something like this. So the point is, in this, this S is basically the union of, let's say, S sub I, I equals 1 to n, where each face, S sub I, is, planar. Okay. So you can imagine such a thing, right? And if you think about that, the idea we're going to go with here ultimately is that if you had some more curvy space, right? If you had some kind of like curvy space, then you could imagine fitting, like a planar approximation inside that curvy space, right? And if you take enough panels, you can get closer and closer to the curvy space by using this like planar approximation, right? Just like we talk about approximating a smooth curve with a piecewise, like a broken line segment, Similar idea, but for surfaces. We could replace the surface with a bunch of polygonal faces suitably inscribed in the surface. And what I want to explain to you right now is that Stokes' theorem is pretty clearly true for such a surface that's built from these planar faces. And the essential point is just this, is we proved before that the Green's theorem, the boundary of a region of P dx plus Q dy, what was it? It was equal to the integral over the region of partial Q partial x minus partial P partial y, right? dA. But what is that really? What that really is, if we want to put it in a more coordinate-independent language, that's the integral over the boundary of S of f dot dr is equal to the integral over the surface of the curl of f dot n hat du dv. See, because really you could think about this as being, f equal to p q r, and this of course would be del cross f dot z hat, right? And then like in here, the dr was what? It was dx comma dy comma 0, because there's no z in we're looking at this is r, right? So who's to stop you from reproducing this derivation that we did for Green's theorem, where we make new coordinates, right? You just think about any face in this polygonal thing, and imagine creating x, y coordinates in that face. Right? In that face, you can apply Green's theorem. Right? So like, to apply this theorem to this face right here, what do? I just imagine putting a little, z-axis here and make the y and the x-axis there. So I can view that particular face as a subset of R2. And then I can apply the divergence theorem we already proved, the Green's theorem we already proved, to say that the integral over that face, of the boundary of that face, is equal to the integral of the normal component to the curl over that face. But there's nothing special about that. I can do that for every single face, right? So what I'm trying to say is we could just as well put a sub I here, and so show that this is for each I, 1, 2, all the way on, however many faces I got. And then the neat thing is, when you take the sum of these results over all faces, what happens? Like, what's the sum I equals 1 to n of the integral over the boundary of Si of f dot dr? Well, that's going to be equal to the sum I equals 1 to n of the double integral over Si of the curl of f dot n hat. And I really should say n sub I hat, because they have dependence on I, right? There probably should be a u sub I and v sub I there too, if I'm going to be picky. But the larger point here is, if you really look at what we have, and you sort through the definition, you'll see that all we have on the right-hand side is just, that's nothing more than the surface integral of the curl over this polygonal thing. Because to calculate the surface integral over a polygon, we do the surface integral on each face and add them up. But that's exactly what we have on the right-hand side. So this, on the right-hand side, we have the surface integral over S of the curl. The kind of interesting thing happens on the left-hand side. All right, so let me go back to my picture here. And, well, actually, let me start afresh, if you will. It's easier. So suppose I've got, here's my, I'm going to make it big enough so you can see it. So here's a few faces. Let's see what happens. Let's see, I guess I can't. I probably need one of these. And one of those, something like. Anyway, there's some faces. So let's talk about this being, for the sake of enumeration, S1, S2, S3, up here, S4, S5, S6. And these are supposed to be outward oriented. It's like, what's the boundary of S1 look like? I'll use red. The boundary of S1 goes like this. What's the boundary of S2 look like? I'll use green. Again, outward oriented, normal. Right-hand rule tells me I have to go like that. So, oh, that's interesting. Look at that. What happens to these the interior joins? When the faces join together in the interior of the polygonal thing, those are equal. They're going to cancel. They'll cancel, right? And if you were to look at up here, let me use brown, what would the boundary of S4 look like there? Look at that. So this S4 has an interior boundary, which also cancels with the top of S1. And over S3 here, you see it's got its interior edge cancels with S2. Right? And in fact, S3, if we could keep going in our mind's eye and see around the back of this, there'd be an interior other face back there that it would cancel with, unless S3 is actually on the actual honest-to-goodness boundary of the surface. And likewise up here, these also give you things which cancel on any interior edge. If you look at where two faces join together, you're going to have a cancellation of the line integral. So sorting through that, as you add up all of these integrals over all of the edges, what's left is the integral over the boundary of S itself. In other words, the actual honest-to-goodness edge of the surface. All these interior edges cancel, and it leaves us with that. And that is the Davy-Stokes theorem, which says that Stokes' theorem is true for a polygonal surface. And it's really just Green's theorem applied to each face, pasted together. Now, how do you prove the honest-to-goodness Stokes theorem from this viewpoint? How do you get from a piecewise approximate surface to the real surface? What do? What do we always do in calculus? Yeah. Right, take infinite s sub I. Just make your partition smaller and smaller and smaller and smaller. We'll get closer and closer and closer. And this argument is true at every stage of that approximation. So in the limit, we get the honest-to-goodness Stokes theorem. That is the argument. But to put pen to paper on the analysis that we just outlined is way above our pay grade in here. Like, to deal with those limits explicitly. That's pretty sophisticated analysis. We don't actually do that. If you look at my notes, I think I have a proof of Stokes' theorem for like a graph, right? So I have a proof for a graph in the notes, which you can look at. I like this argument, though. I think it's important to see it. So then the next thing to prove is, of course, the divergence theorem, right? How do we prove the divergence theorem? So the proof of Stokes' theorem for a graph, which is totally uninspiring, is page 371 to 372. It's there in gory detail. You can look at it. Actually, it's 371, 372, and 373 are all proof of Stokes' theorem for a graph. Blah. Let's look at Gauss's theorem, though. Okay. And so what I want to do is I want to think about like a little... What's it? It was not about Calculus 3, was it? Aha! It wasn't sports, was it? Oh, it was sports! That's worse. Tell me it was about... Well, anyway. I digress. So... all right, so suppose we thought about like a little, think about like a little pillbox, so to speak. It's like a little cylinder, and I'm going to try to fix this. In my notes, I don't like it. I got dz here. I'm going to put delta z here for like a little finite z. Let's suppose that the bottom face is at z naught, and so this is at z naught plus delta z. All right. And what I want to try to do is to look at the integral. Okay, so first of all, what do we already have to work with? We already have to work with the divergence form of Green's theorem, which says the integral over the boundary of D of, px hat plus qy hat dot n hat ds is equal to the integral over D of partial p partial x plus partial q partial y dx dy. And so I'm going to look at, on a cylinder, the cylinder I'm looking at is actually, I'm going to call it E. Essentially, it's this disk D Cartesian product with this little delta z. If that's bothersome to you, I have pictured it. Okay? I have pictured it. Let's see here. So to a pretty good approximation, where's this n hat in my picture? I mean, you could pick either one of these, but the n hat is the outward normal to the circle. Right? So this is like, this right here would be ds. Okay, the little arc length around the circle. And you could do the same for the upper face, actually. In fact, since we're looking at a cylinder, I can do this for any slice. I can apply Green's theorem, divergence form of Green's theorem at any slice for the vector field px hat plus qy hat dot n hat ds, and it's equal to that. So if you like, really, what this is at the moment is, that gives me the number of field lines. This right here gives me the number of field lines that are going out this lower circle, right? So you could do that for an arbitrary circle in here, which is really what I want to think about. I'm applying this at an arbitrary, really this is at, z, at z. So here z is an element of, between z naught and delta z, z naught plus delta z, right? It's for some disk in there. I'm applying the divergence form of Green's theorem to count the number of field lines that are going through that circle. Right. So that would give me just an infinitesimal, really. This would give me the change in flux, right? That just gives me that gives me the number of field lines just going through one of those circles, right? So if I wanted to add up the total number of field lines going through the entire curved surface, what I need to do is integrate that from z naught to z naught plus delta z, right? So basically I should integrate, delta phi over, z naught to z naught plus delta z. Of course, this is integration with respect to z. Add that up anyway. I don't know how to say this. The sum these up over the side. And it should be somewhat clear to you that should mean we integrate from z naught to z naught plus delta z of this thing. All right, now you need to use your imagination a little bit. This right here is nothing more. If you look at, I'm missing my dz, right? So what's dz ds? If you were to take a little patch right here on the side, right? And you were to look at that patch, you'd have dz like this, you'd have ds like this, n hat's pointing out like that. That's nothing more than the infinitesimal vector surface area element to the cylindrical side to the disk. To the cylinder. That's the vector area element pointing out of the side. So what is this? What did I do? Oh, Q has no hat. Yes, thank you. Too many hats. Wearing too many hats. It's always a problem in life. But hey, we could do this. Plus r z hat. That wouldn't change anything, because what's z hat dot n hat? It's 0 by construction. So if you look at it, what we really have here is p comma q comma r dot ds vector. Integrate over the side is equal to the triple integral triple integral over the E of what? Partial P partial X plus partial Q partial Y. Right? I forgot my dz. Oops. Now that's not quite Gauss's theorem yet. What are the other two pieces that contribute? So yeah, we've got the field lines coming out of the side, right? So at the moment, my argument has counted all the lines that are coming out like this, right? These kinds of field lines. And one's out the front and so forth. But we also have to think about the top and the bottom, right? So, you know, you got up here, ds is dx, dy, z hat. And down here, you've got ds, we call this ds top, ds bottom, the base, minus dx, dy, z hat. Right? So we should also add those in, right? What's the integral over the top? We have integral over the top of what? Of P comma Q comma R dot ds top plus the integral over the base of P comma Q comma R ds base. That's what's missing as I've currently, I mean, I need to calculate that as well. To be fair, the flux over the cylinder, we got two pieces, the one through the curved side, the flux through the top, the flux through the bottom. Now, what does this actually look like? So this is the integral over D, Cartesian product with z naught plus delta z, right? And what we actually got here, we've got r of x comma y comma z plus z naught plus delta z, right? And we're integrating over dx dy. And then we've got plus, well, I should really say minus, right? The integral over d Cartesian product with z naught, that's the base. And what's that actually? That's actually r evaluated at x comma y comma z naught. The minus because of the direction. So what you're actually looking at here is the triple integral of partial r partial z at x comma y comma z dz dx dy. And this is from z naught to z naught plus delta z. What did I just do there? I mean, if you like, let's see here. Well, I mean, fine. Let me rewrite it this way. This is, we can rewrite it as such. Erase the dx dy. Erase this. We really have this minus that. So my point to you is that the change of r at x comma y of z plus delta z minus r of x comma y z naught, that is equal to the integral of the derivative of r with respect to z, holding x and y fixed at z, over dz from z naught to z naught plus delta z. This is just the net change theorem calculus. So what's that say? That says that the flux through the top and through the bottom, those account for the integral of the z part of the divergence. So then what you do is you add together, what you got to do is you just got to add, let me give it some names. Let's call this star star. All right. Add star star to star. So if we take star and we add it to star star, what do we get? we get the integral over the boundary of E of P comma Q comma R dot ds is equal to the integral over E of what? Partial P partial X plus a partial Q partial Y plus partial R partial Z dV. Put in much better terms, what we have is that the integral, the flux integral over the surface of the positively oriented pillbox is equal to the integral over the volume of the pillbox of the divergence of F. And that, of course, is Gauss's theorem. So indeed, Gauss's theorem also can be derived from Green's theorem, the divergence form, by considering an appropriate solid and doing usual arguments. But not everything's a pillbox, right? Like we applied Gauss's theorem to a cube. So how do you, I mean, you could prove Gauss's theorem for a cube, actually. It would be not much different than what we just did. If we were doing it for a cube, we'd actually have to, like, you could do it for a cube. You just have to look at, like, square slices instead, right? You could see how this argument would work for a cube just the same, right? What you'd do is, like, look at a square. You'd look at, like, a square. You apply the divergence form of Green's theorem to a square, right? And you can do that, you know. You do it for a square, you do the divergence form of Green's theorem, you add up from the top to the bottom, add up over the cube, you'd get the flux through the vertical faces is equal to the integral of partial P partial X plus partial Q partial Y, and then you take the difference of the flux through the top and the bottom face, and again, if you make the cube small enough, like, not really a cube, but if you actually did it for a slab, it would be more appropriate, right? Think about these faces being close, then this step is legit. There's something I'm glossing over if you go into the details more. But my point is you could generalize the argument we just did for a cube, and then what if you have a simple solid, right? What if you have a simple solid, like a donut? What could you do with a donut? You could take, and you could put like a cube in the donut, right? And then, my bad picture. And then you could take like another cube out here, right? And you could just start filling the donut with cubes, right? And you got I mean, this is a horrible picture. But my point is, if you could think about some sort of simple solid, you can imagine filling it with cubes, right? Maybe I've got a better picture in the notes. I'm kind of scared to look and see if I have a better picture in the notes or not. And what happens so we have I've sketched for you at least a proof of Gauss's theorem for a cube. If you take a simple solid, you can break it up into like a union of cubes. That gives you a good approximation. What happens when you apply Gauss's theorem on such a union? You get that the flux of interior faces is equal and opposite. It cancels out just like we saw for this argument over here. Because wherever these cubes meet, right? I mean, let me just make it a little bit more specific. Suppose you got these two cubes meeting inside your cubical approximation for your solid. At that interior face, what happens? Each cube has positive orientation, so like this is the normal for that, so this one has normal like that, normal like this. So the other cube, though, also has positive orientation, which means that it's got normal like that, and normal like that, and normal like this, and normal like that down there. So any interior face, you have equal and opposing fluxes. The fluxes at any interior face cancel, and all you're going to be left with, ultimately, is the exterior, like the edge, the flux through the actual edge of the simple solid, which is why we get Gauss's theorem as we do. So anyway, I find it very intriguing that almost the same kind of chopping it up into little polygonal pieces for a surface still makes sense for chopping of a solid up into like chunks, right? And applying Gauss's theorem to each chunk, and then like adjoint faces in the chunk, in this, you know, chunky approximation to the solid, they're still going to have the cancellation, but this time not of line integrals, but of flux integrals at adjacent faces for Gauss's theorem. All right. Well, I have done my due diligence. I have proved, or tried to prove these theorems for you. Sometimes this drags over about 3 days. I thought I'd just rip it off like a Band-Aid this time. If you have further questions about the proofs, you can come talk to me. But I thought I should do this. Now, in the notes, I may feel guilty about this day, looking forward. I may feel like I need to give you further proof. There are specific gory proofs for specific cases. Like, for a simple solid, if I have the solid described in sort of the most natural way in terms of like being bounded by a graph, z equals f of xy, and then I think a cubical domain, a square domain for x and y, I've got a proof in that context as well, sorting through the calculus line by line. None of this approximate geometry stuff I'm doing. But I think the approximate geometry stuff is better because it actually gives you some sense of why these theorems are true, and how also they're part of a larger story. Do you see that the proof I've just sketched for you is so much the same for Stokes and for the divergence theorem? They really are both built over this idea of chopping spaces up into subspaces which have some kind of internal cancellation of faces. That is actually the part of a start, that's the start of a much longer story. Anyway, for another day. Do you guys have any questions about your homework then? Because, I mean, I could work an example of Stokes' theorem or something at this point, but I'm going to erase the evidence. What's that? Which mission are we on? 8. All right. Actually, I'm very curious now. Do I actually have a picture that's worth anything in the notes for the?
It's rather funny that you do have though.
Oh, it is? Huh. I'm intrigued.
Page 377.
Oh, there was other things I was going to do today. You guys can bring me your, since you don't actually have a homework question, you're just trying to think one up right now. I judge from your reaction to my question. I mean, if someone had a homework question, they'd be like, I have a question. But you guys are like, what's in the homework? Which is not the reaction I was looking for. Don't have your homework with you. Okay, fair enough. Well, this is a bad choice of color, but there's actually things going on there. So a couple things in the notes that I have neglected to prove or mention to you yet. One of them is just the definition of surface area and surface integral. It begs the question of parameterization, like I used a parameterization to define it. So what would happen if you changed parameterization, right? What if instead of using U and V as a parameterization, suppose I used, a different parameterization, say A and B. So in other words, reparameterize the surface. What happens to the surface integral formula? Well, that is a rather pesky problem of chain rules. Basically, I would have to rewrite x, 1, 2, and 3 as functions of A and B instead of U and V. And each one of those gives me a chain rule. No one in their right mind ever covers this in class. We just say, hey, it makes sense. And you guys never say, hey, but what if you used a different parameterization? And how would you know the answer would be the same? How dare you? No Calculus 3 student says this ever. So, but anyway, the point is, if you were to change parameterization, this would be the relation between the partial derivative with respect to the U parameters versus the A and B parameters. And likewise, V as it relates to A and B. And when I actually calculate what we have, the U coordinate velocity as it relates to the A and B coordinate velocities, we get this. We actually end up with partial x, partial a, partial h, partial u, partial x, partial b, partial g, partial u, where h and g are the reparameterization maps. And then something really neat happens when you actually take the normal vector with respect to the new parameters as it relates to the old parameters. Well, the new normal vector field calculated in UV parameters versus normal vector field calculated in AB parameters, the relation between the two is just this pesky partial h, partial u, partial g, partial v minus partial g, partial u, partial h, partial v, which just stinks of a Jacobian, does it not? And in fact, that's exactly what you need to change the integral, change from a UV integration to a AB integration. We need the Jacobian that changes from UV to AB. And that's exactly, H and G are my notations for A and B. That's exactly what we have here. So this is what I need in order to make the change of variables theorem. And so there you go. It doesn't matter if you calculate the surface integral with respect to one parameterization or another. You always end up with the same answer, provided that it's a consistent reparameterization. In other words, that you haven't turned the normal upside down. Well, anyway, there it is. All right, so I have assuaged my conscience. Now we've seen the proof of that. Here, see, I think I did a good job on this one. Like, this is better than what I wrote in class, right? That one's pretty good. How about the other one? Ooh, for holes, I'll talk about that again some other day. Ooh, more holes. Here's the proof for a graph. Great. Here's the thing. I think I improved this in class today, by the way. So I chickened out, huh? Did I chicken out? Yeah.
In the notes that you published for us, the picture that's there just says should include picture here.
Oh. Oh. Yeah. I mean, I know what I want to draw over here, but I've never been successful in like really drawing it. Certain semesters I get closer. But how do you draw a three-dimensional, like amorphous, like a curvy solid with a like a cubical approximation inside it, you know? It sounds like a whole episode of that show they used to have on PBS with the guy who would like draw the little, remember the guy who sit on the chair and show you how to draw things? Never mind. We have a different past. Okay. All right. Anyway, and so what's happening? Oh, here it is. So here is a straight up proof of the divergence theorem for a cube. All the gory details right there. Yay. All right, anyway, I'm going to put this away. Oh, you got a homework question? No? Yes? Let's look at mission 8 together. And
Explain the last question. That's just 120. Yeah.
if I can find mission 8, where'd I put that thing? Yeah, that's the wrong kind of file. Look at mission 8 solution. You guys are funny. All right, so here's a thought. Just looking ahead. Surface area of a torus. So you've got a big radius and a little radius. What would be the coolest possible answer? Zero. Oh, I guess I don't know. Never mind. I think it would. I was thinking like, what if it was the circumference of the outer circle times like the radius times the circumference of the little circle. Like if it was wouldn't that would make sense, right? I mean, circumference of the outer circle times the circumference of the inner circle. If that was the answer, that'd be neat, right? So 2 pi r times 2 pi a. I don't remember if that's actually the answer or not, but it would be neat if it was.
Do we get points from
I mean, you should actually calculate it. The point of this problem is to work it out. How do you work this out? You got to calculate partial x, partial alpha, partial x, partial beta, take the cross product, go from there, right? Then you get, well, anyway. How about this one? how should you do this one right here? I think we're talking about outward-oriented unit sphere. Unit sphere, well, we know what ds is for that, right? It's r squared sine phi rho hat. So let me suggest that you use that and convert this to sphericals, I suppose. Right? Well, maybe not convert that to sphericals. Maybe just, well, anyway. Can anybody think of a lazier way to do this problem? What's the divergence of x cubed, y cubed, and z cubed as a vector field? It is 3x squared plus 3y squared plus 3z squared. Wait a minute, the divergence is 3 rho squared. So if you use Gauss's theorem in spherical coordinates, problem 108 is like 3 lines. So Gauss's theorem is nice for problem 108. I still think you'd get something out of it if you calculated it directly, but you don't have to. You could use Gauss's theorem there. How about 109? Oops. Wrong button. Thin shell of constant density delta. So I probably would have used a sigma in here for that when we talked about things in class, right? Sigma was the mass per unit surface area. Shall be cut from the cone. There it is. This and that. Find the center of mass and the moment of inertia with respect to the z-axis. So, that's, there's 4 integrals to do there, maybe 5. You got to calculate, first of all, the mass, right? Then you got to calculate the integral of x delta dm, y delta dm, z delta dm, all divided by 1 over m. Does give you x bar, y bar, z bar for the center mass. Then we also have to integrate x squared plus y squared times dm to find the moment of inertia about the z-axis, right? So we talked about these. There's a bunch of stuff to do here. I think the smart thing to do, though, would be to notice that this is a cone. It is the cone x squared plus y squared equal to z squared, which is the standard cone, which has what? Like the lines z equals x or z equals y on the sides of it, right? What's the angle? I believe this is the 45-degree cone. Sort through it. So we've already calculated the ds surface area element for this for the cone. It's one of our standard examples. You can use that. Find the flux of this thing through the parabolic cylinder, blah, bounded by this, this, and this. I don't think we have any cut and dried formulas for here. You're just going to have to work through it. You have to parameterize the cylinder and work it out. How would you parameterize the cylinder? What would be a good parameterization for the cylinder? May I recommend? Parameters, what? Oh, wait a minute. I take it back. Maybe this actually is a graph. Is this a graph? Well, it's a graph. Part of it's a graph, but it's a little bit more than that, right? Can we draw a picture of this? Let me help you out, guys. Think about it. Can you guys hit the lights for me? Let's see here. We have, what was it? I lost track already. Z equals to 4 minus y squared, right? Bounded by what? All right, so this is basically like that here, right? It's 4 minus y squared, so it opens down, but we've got, oh, wait a minute, x equals, oh, it does go back over here, doesn't it? Z equals 0. cuts it off down here, though, right? So what I've drawn so far is just the intersection of the surface and the YZ plane. And then what's it do? It goes all the way over to x equal to 1, right here, right? Let's say. And z equals 0, so it's kind of like this deal, right? So if I could, it looks something like this. Parabolic cylinder, bounded. Assume the orientation of the surface is outward. I'm not sure that actually makes any sense. Oh, away from the x-axis. All right, now I'm on board. That's unambiguous, right? Because the x-axis is down here, right? So we're talking about the orientation being like this. I think this is actually a graph, so you could use the graph toolbox, right? F of x comma y is what? 4 minus y squared. So you can calculate the flux of the upward oriented parabolic cylinder in view of that. What would the domain? So here's the parameterization here. I would say x, y, and then what was z? 4 minus y squared, right? This much is clear. 0 less than or equal to x, less than or equal to 1. How about y? I mean, you can see it in the picture, right? But you don't, I mean, what is that? What are those? This is y max. Down here is y min. Oh, you said minus 2. And so how did you guys get that? Minus 2 and 2? Oh, you put z equal to 0 and solve for y, right? That's where it's at its maximum extent in the y. Cool. All right, well then you got to calculate the surface integral there. We've got the flux of this pesky vector field through the conical frustrum between the... Okay, so conical frustrum is just a fancy way of saying it's... What is that stupid thing? Square root x squared plus y squared. Z... what does that look like? I think it's basically this deal. And what's the orientation? Outward. Through that, between the planes. Now here there's an ambiguity. Are we talking about just the conical frustrum? Or are we talking about the closed solid that's bounded by these things? I think we're just talking about the conical frustrum. So actually, it's an open surface is my point. It's just this, right? So it's like this piece here, and of course the back. In contrast, you could think about the solid one, which has the top and the bottom as well, and the sides. That one would be nicer in some sense because... So the question, I believe, is just talking about the red part. I'm telling you it's just about the red part. I made the problem up, right? Why would the closed surface, the surface with no hole, be nicer? Because we could apply the divergence theorem and swap it out for the integral of the divergence over the volume. By the way, there's some thoughts to get you started. So tomorrow, I should give you guys some daily quizzes, I think.